Welcome to Chemical Process Safety. This video is about hazardous quantities of toxicants. Last time, I told you about the interesting philosophical principle of toxicology, which is that there are no harmless substances, only harmless quantities of substances. But how would you go about determining what a harmless quantity is for a given substance? The easy answer is to just look it up, but there are several different measures published by several different sources, and it depends on exactly what your definition of harmless means. Perhaps the most conservative is the TLV-TWA, which is an acronym that stands for Threshold Limit Value Time Weighted Average. This is defined as the quantity of a toxicant that wouldn't have an adverse effect, even if a worker were exposed to this concentration for the entire 8-hour workday, day after day for an entire working lifetime. A little less conservative is the TLV-STEL, which stands for Threshold Limit Value Short-Term Exposure Limit. Workers may be exposed to toxicants at the TLV-STEL for up to 15 minutes at a time for no more than 4 exposures per day, provided that there is at least 1 hour between the exposures. Provided that these guidelines are met, a worker should not experience irritation, irreversible tissue damage, or impaired function. Less conservative still is the TLVC, or Threshold Limit Value Ceiling. This is the upper bound, and workers should never be exposed to toxicants at this level. For example, here are the TLVs for ammonia. The TWA is 25 ppm, or parts per million. The STEL is 35 ppm, and the C is 50 ppm. TLVs are published by the American Conference of Governmental Industrial Hygienists, which is a professional society. It's important to note that TLVs are meant only as guidelines and do not have the force of law behind them. In contrast, the PEL, meaning permissible exposure level, does have the force of law, and companies may be subject to fines if these quantities are exceeded. PELs are set by OSHA, and since I haven't mentioned them in a video before, I'll introduce the acronym as the Occupational Health and Safety Administration. If you're involved in chemical process safety at all in the real world, you'll get to know this regulatory governmental agency very well. The IDLH is yet another quantity that you might see. This one means immediately dangerous to life and health. Although this one's name is pretty self-explanatory, let's define more specifically. This quantity is likely to cause death or immediate or delayed permanent adverse health effects or prevent escape from such an environment. You may be wondering how the people who publish these values actually know what concentrations will produce a given effect. After all, it's not like they can perform experiments to find out like other scientists would, because of the moral and ethical problems with exposing people to toxicants in the name of science. Experiments on model organisms can be extrapolated to humans, but more complicated still is the fact that different individuals will respond to dosages differently. Responses typically follow a normal distribution, or bell curve. You can quantify the response by calculating the mean and standard deviation, as you likely learned in statistics. If the experiment is repeated for several dosages, you could plot the response as a function of the logarithm of the dose, and the result is called a dose-response curve. The response that you're measuring can vary, but lethality is a common one. The dose that results in death for half of the subjects is called the LD50, shorthand for lethal dose for 50% of the population. You'll commonly see this value reported in safety information for toxicants. Of course, death is the worst consequence possible, so the LD50 should be a bit higher than the reported TLVs, PEL, or IDLH. You'll notice that the response versus log dose curve is not linear, but rather sigmoidal. One way to model this function is with the Probit equation, which is a portmanteau of probability unit. A reason you might do this is to calculate the percentage of individuals who would exhibit a particular response upon exposure to a certain dose. This is the equation that you'd use. Don't worry, you won't actually have to perform this integral. I'm just showing you the actual equation. This says that probability is a function of y, which we'll call the Probit variable. In turn, the Probit variable is a function of the natural log of dose. Here, K1 and K2 are fitting parameters, and V is the dose. Refer to Table 2.5 in the Crowell and Luvar textbook for the values of K1 and K2. Pay careful attention to the footnotes, which tells you the units that you'll need. Once you have the Probit variable y, you can convert it to a probability using this function in Excel. Probability equals 100 times norm.s.dist. arguments are y minus 5 and true. And if you wanted to work backwards instead, that is, calculating the Probit variable for a given probability, you'd use this function instead. Y is equal to 5 plus norm.s.inv, argument is probability over 100. Alternatively, you could just work between probability and Probit variable by referencing table 2.4 in the Krall and Luvar textbook. How about an example? Let's compare the toxicity of carbon monoxide, hydrogen chloride, and phosgene. In this spreadsheet, I've already pulled values for the parameters K1 and K2 from table 2.5. To make sure we have an even comparison, let's pick the same concentration and exposure time for all three. How about 200 ppm for 45 minutes? Now, I'll calculate the dose by multiplying concentration in ppm times time, as I'm instructed to do by the footnotes of table 2.5. Now, I'll calculate the Probit variable by taking K1 plus K2 times ln of the dose. Finally, let's convert the Probit variable to a probability, using the expression I gave you before. These results show that for a 200 ppm exposure for 45 minutes, you basically have a 0% chance of death with carbon monoxide. You have less than a 1% chance of death with hydrogen chloride, and death is all but certain for phosgene. The benefits of performing your calculations in a spreadsheet mean that you can easily change parameters to see how the results will change. Okay, let's turn the question around and work backwards. What if we wanted to find the LD50 for a 15-minute exposure to phosgene? Recall that LD50 signifies a 50% chance of death. I would convert that probability to a Probit variable using the other formula that I gave you. Now rearrange the Probit variable equation to find the dose. And finally, divide this dose by the time to get the final concentration. The result is 48 ppm. We can compare this to the TLV TWA for phosgene, which happens to be 0.1 ppm, and note that, of course, the LD50 is going to be much, much greater. Keep in mind that the Probit model is only an estimate, so it doesn't make sense to keep track of too many significant figures. That's all for this video. See you next time on Chemical Process Safety.